And it's time for presentation number 4, which is going to be given by Connor. The talk is titled Anonymous Complaint Aggregation for Secure Messaging.
Awesome. Hello. So today we're going to be talking more about encrypted messaging, and in particular, so we've heard what types of systems these are today a lot. So we'll jump right in and think about what can go wrong with end-to-end encrypted messaging. So suppose we have a bad actor, Mal, and she sends some message to Alice, and then Alice forwards it to Bob. So in the source tracking, or sometimes called traceback context, if Bob received this bad message and thought, oh no, I need to report this to the platform, there are mechanisms where Mal could be revealed as sort of the malicious sender in this setting. On the flip side, let's suppose that Mal is the one receiving a good message, or say, just something that they don't agree with. It could be a protest, counter-protest. There could be details that someone would want to invade Alice's privacy for sending this message as the originator of the message. And so that there's sort of two sides to this coin of what makes a message bad. So when we look at these schemes, some of the ones that have historically been done, a single recipient can force the platform to reveal or investigate a particular message, and instead we can consider threshold reporting. So n number of users would have to report the same forwarded message before the platform would sort of take any action. This tries to provide a balance between a single user objecting to something, but also recognizing that if a large number of users are finding something objectionable, that it's possible that it is indeed false information or hate speech or something of that nature that should be investigated and put to an end. So stepping back, is this really the right problem and the right solution to sort of think about? One consideration is government regulation. End-to-end encryption is under a lot of pressure from various governments, and this could be one potential compromise that would show that we could run platforms that would have ways of detecting sorts of bad content and preventing it from proliferating, or certainly learning if it is proliferating. There's out-of-protocol usage. So in the prior examples, we talk about forwarding. For example, you can work around this by copy and pasting a message, or using a different account, and so there are out-of-protocol things that this forwarded use case in Aggregate doesn't really cover. There's Sybil attacks, where suppose you receive a forwarded message once, and you can acquire a bunch of other accounts on the platform. You could report the message a bunch of times. So that's worth considering. And then also, we heard earlier about metadata hiding platforms, which this does not work with. And also thinking about what should actually be revealed. Should we reveal who sent the message, or simply just the notion that the message was revealed? So that there's a few different things that can be factored in with this. So when we talk about aggregating complaints, we're specifically talking about a signature coming from the platform that is forwarded along with the fresh ciphertext every time. So the platform isn't aware necessarily that this message is being forwarded, but every recipient of the same forwarded message will hold two things: the plain text of the message after decrypting it, and some original metadata that's signed by the platform. And so those two things allow us to have sort of a consistent view of the message that we can actually count in a histogram. There's one prior work in this space, FACS. They use collaborative counting Bloom filters, where each bin belongs to one or more messages and one or more users. And essentially, the users looking at sort of this array of storage can learn approximately how many users have reported a message in question and alert the platform to that fact. There are a few drawbacks with FACS. The first is that counting is approximate. And that goes along with the second caveat that there's parameter tuning. You can try to minimize the error, but it is very particular about how you can align how many messages you expect to be reported, what your current user traffic on the platform is looking like, and things like that. Additionally, a user can report a message potentially more than once, and the platform won't be aware of this. And then lastly, with deniability, since those bins correspond to messages and users, and the platform knows which user is reporting, it's possible for them to reconstruct after the fact which user actually reported a message with some probability. So we present a two-server solution, and the intuition is that the first server is going to learn who is reporting messages, and the second server is going to learn which message was reported. So with the first server, the user is interacting, they're verifying their identity, and they get back an anonymous token that they're able to use for an interaction, an anonymous interaction with the second server. This is handled in a shuffled batch, where they can actually specify which message in particular they intended to report. The second piece of this is that a verification between the two services that the threshold was actually reached for a message. And so the second server, which is keeping essentially a histogram of those hash of reports and how many users have reported, can actually prove back to the first server one message out of many corresponded to a single vote for the message in question that it wants to prove the threshold was met for. So when we think about our security goals for report uniqueness, we assume that the first server is honest because the first server is in charge of identity verification, but there can be any number of malicious users, and we show that they can't report more than once. For reporter anonymity, the first server knows the identity of the reporter, so we're essentially preventing the second server from learning the identity of an honest reporter. And then inversely, with reporter confidentiality, the first server knows the identity, but we're preventing it from learning the contents, or specifically which identifier of the message they wanted to report. So our scheme, the anonymous tally, is in a couple of phases. So essentially, the client interacts with the first server via an oblivious PRF to sort of get part of the computation that we want to compute, which is essentially a unique identifier that for this user reporting this message, we have a value, but it's a little bit different from that because the client adds an additional private key masking term, and that is where we're sort of introducing a user-specific value to this identifier that will later get used in the counting. All of these communications are verified with non-interactive zero-knowledge proof of knowledges. And then the user gets back a MAC token on the statement of this PRF evaluation so that it can then prove to the second server that essentially this interaction occurred. Then the second server is sort of able to get all of the actual components, the true inputs to the oblivious PRF. And then if everything checks out, it increments the count and holds on to that for later. And so S2 is getting these in shuffled anonymous batches, so it's not able to learn which users are actually reporting and what, for instance, their public keys are. And then for the verification, so I alluded earlier to we're trying to get a unique identifier that corresponds to a user reporting the message. That's how we do duplicate prevention. So this dupe tag is essentially the hash of report raised to X, which is a user secret, and Y, which is a server secret from the first server. And so this dupe tag would always be produced if the user attempts to report the same message more than once going forward. And then for the proof that the threshold has actually been reached on the second server back to the first server, we essentially use Sigma OR protocols to show that one report, which the first server would have seen, mixed in with in other reports, of which the prior interactions would have also been seen by the first server. One of those will honestly count towards the threshold, and so we're able to sort of mask the report. And additionally, if the platform doesn't have enough organic traffic for this to happen, then cover traffic reports can be generated where users just report bogus messages, and this would provide additional privacy for users who really wish to report messages. So we evaluated our scheme, and in particular, I want to highlight that we were able to get away from the array of storage, which had to scale relative to the number of users and messages expected to be reported for a certain period of time, to constant communication costs per report, as well as constant computation times, and in particular, the protocol for reporting a message between the client and the first server takes well under a millisecond to compute. I've presented the two-server approach, where essentially the first server is learning the identity of the reporters, and the second server is learning which messages are reported. And we've sort of formalized these additional properties that we'd like for reporters, including report uniqueness, reporter anonymity, report confidentiality, and we've also arrived at an efficient implementation of this that could be is workable for a system in practice. Thank you.
Are there any questions? Okie dokie, I suppose I have questions. So this method relies on two servers that are not colluding. This is commonly seen in practice across differential privacy, also other fields. But in practice, there's also the concern that if you convince a service company such as Facebook or WhatsApp to deploy this, that they'll end up just hosting both servers. So is there some sort of incentive structure or a way to maybe get additional guarantees on non-collision of these services and ensuring that they're deployed across different actors?
Yeah, sure. We've thought about this a little bit in practice. I know that like some other systems, such as like COVID exposure detection and sort of some other like practical systems, also have this model of non-collusion between two services. I think we're certainly envisioning that the first server most organically could be hosted by the platform, which then certainly means that the second server should be detached in some way. So it's unclear if that third party should be a government agency or some other. I think that would probably be the most natural step, but we don't have a specific proposal for ensuring that non-collusion. I think we leave that to other work.
Okay, thank you very much. Let's thank the speaker one more time.